Hey y'all, it's Ms. Blasky. We're going to go back in time a little bit and talk about topic 8.5 today. So previously we talked about using two different methods, which are both considered to be part of Hess's law, to find the enthalpy for a reaction. Today we're going to talk about a totally different way to find the enthalpy of a reaction. Now, if I did multiple different methods for the same equation, the same chemical reaction, I should get the same answer. It all just depends on what data we have available to us. So today we're going to talk about the idea of bond enthalpy or bond energy. So when we have chemical bonds, we must put in energy to break bonds. Breaking bonds is an endothermic process. When we form new bonds, energy is released. That is exothermic when we form bonds. People get this backwards all the time. And to be totally honest, if you look in any biology textbook, they probably explain this the opposite direction, which is really annoying and really frustrating to chemistry teachers. So you have to remember, it takes energy to break bonds, and you form energy when you form bonds, right? So another way that we can find the enthalpy of a reaction is if we know how much energy is stored up in those bonds of each of the chemicals in our reactants and our products. So to find the enthalpy of reaction using bond energies, we take the bond energies of the bonds that are broken minus the energy of the bonds that are formed. Now, if we are breaking bonds, the bonds we are breaking are going to be in our reactants. If we are forming bonds, we are forming bonds in our products. So technically, this is the bond energies of the reactants minus the bond energies of the products. Now, this equation is not on your equation sheet. I don't know why, but it's not. And it is the reverse. It is backwards of the Hess's law delta H, where it's sum of the products minus sum of the reactants. This one is backwards. You need to remember this, all right? So not only do we need to think about which bonds we're breaking and which bonds we're forming, but we might need to think about the structure of those molecules to figure out what bonds are actually messing around. So if we take a look at example number 26, fairly simple, straightforward equation. Hydrogen plus fluorine makes HF. So let's think about what bonds we have in all of these molecules. So H2 is an H bonded to another H. F2 is a fluorine bonded to another fluorine. Those are both single bonds. HF is a hydrogen single bonded to a fluorine, but we've got two of them, right? So sometimes it helps to draw these out. Sometimes you might have to draw the Lewis dot structure to figure out how many bonds are being moved around, right? So to find my delta H, I need to figure out what bonds I broke. Well, I broke one hydrogen-hydrogen bond, which its bond energy is 432. And I broke one fluorine-fluorine bond, which is 154 kilojoules. And I formed two HF single bonds, which is 565 kilojoules per mole. So again, just like when we were doing Hess's law, we still have to multiply by however many bonds we have. We still need to be very careful of signs. So 432 plus 154 minus 2 times that 565 gives me an overall answer of negative 544 kilojoules. So when we get into much more complicated molecules or complicated structures, you're going to have to really pay attention to what bonds you're breaking or forming and how many of them there are. So This is a table taken out of a generic textbook. For all of your homework problems, you should be able to find everything you need on here if it's not specifically given to you in the problem. Most questions on the AP exam will give you sort of a mini version of this table, just like they did up in example number 26, of either just the values that you need or the values you need plus a couple extra to throw you off a little bit. So when we look at this data table, if we look at all of these bond energies, we can see that we have a couple different patterns that go along. So one pattern we can see is if we look at the hydrogens bonded to different things, especially as you go down a group on the periodic table, fluorine, chlorine, bromine, iodine are all halogens. That bond energy decreases as we go down that group. Why? Think about that for a second. As we go down a group on the periodic table, especially in those halogens, we are increasing the size of the halogen atom, which means that that hydrogen is farther away from the iodine than it is from the fluorine. It means that that bond is not as strong, it's not as attracted to the iodine, and so there is less energy stored in that bond, meaning that it takes less energy to break that bond apart. This is going back to stuff that we talked about when we talked about periodic trends. So things to keep in mind. That same pattern can be seen with several other types of bonds. We also can see patterns in terms of single, double, and triple bonds. So for example, if we look at the carbon-carbon bond, a carbon-carbon single bond has a bond energy of 347. A carbon-carbon double bond has a bond energy of 614, and a carbon-carbon triple bond has a bond energy of 839 kilojoules per mole. This hopefully should make sense with what we know about how those double and triple bonds are formed. In order to form a double or a triple bond, we need to share multiple pairs of electrons. Excuse me, bringing in those other pairs of electrons, sharing other orbitals of electrons, make those bonds much stronger, much closer together. So it would require much more energy to break them. It also means that it generates a lot more energy to form them. So thinking of all of that, go ahead and give number 27 a try. And I'm going to work it out too. You take some time and work it out, and let's see if our answers match. All right, for example 27, I got an answer of negative 1,194 kilojoules. So looking at the structures, I have 4 carbon-hydrogen bonds in CH4. Then I got 2 chlorine-chlorine bonds, 2 fluorine-fluorine bonds for my products. Or for my reactants, and then for my products, I've got in the Freon, I've got 2 carbon-chlorine bonds and 2 carbon-fluorine bonds, then 2 hydrogen-fluorine bonds and 2 hydrogen-chlorine bonds. So this is a case where it pays to sort of sketch out those structures to make sure that you are talking about the right bonds. So then it's bonds broken on my reactant side minus the bonds I'm forming on my product side. So again, we're going to keep working on this, but this is a fantastic way to start to see how some of those throwback topics really are going to start showing up and be very important for what we are talking about. As always, if you got any questions, let me know, and I will talk to you all later. Bye.